Well, our speaker is here. He was able to get Zoom to finally cooperate. So
sorry about that.
No worries, no worries. So let me give a quick introduction, and then I'll hand things over to Drew. So welcome to Peak Hackers. This is our first official meetup of this incarnation of this meetup. It used to be a PHP meetup, but apparently not as many people were interested in PHP as are interested in doing cool things with tech. So I did what all good startups do, and I pivoted. So here we are. We're here to talk about awesome things in tech that we're working on. And with this first meetup, I'm really excited that Drew's volunteered to show off his stuff, because he always works on really cool projects. Not to overhype him or anything, hopefully, but a couple of years ago at the first Colorado Springs Tech Unconference, he showed off a what did you call it? A situational awareness generator or something like that.
Situational awareness enhancement device.
Enhancement device. Yeah. And it was, lights controlled by a Google function or something. It was really cool. Stuff that, isn't the normal stuff that you're just sitting down and, oh, let me hack out a web app or something like that. So I'm excited to see what he has to show us here today. Usually when we're in person, we have sponsors, but since we're virtual, I guess I'm the sponsor. I have a YouTube channel. If you want to check it out, I'll post a link in the, not the description. That's what I say on YouTube videos, in the chat thingy. So you can go check that out. And with that, I'll hand it over to Drew, and let's see what awesome stuff he's working on.
Okay, thanks, Brian. Yeah, so I'd asked Brian actually if I could go next month instead, because the thing I'm going to be talking about is not actually finished or really working. But hopefully there's some good content there anyway. The thing I'm talking about is a hydroponic system that I'm building. I've been wanting to build one of these for a while. Well, now I have a lot more time, like everyone does, right? And also, got kind of hard to get lettuce, if anyone remembers, back in like the month of March or so. And in case that happens again, I figured I'd just grow my own in the most overcomplicated, over-engineered fashion possible. So that was sort of the motivation. So let me see if I can pull up my slides here. Go away.
I thought we were in a lettuce shortage, just to throw that in there. Again.
Oh, let's see. I got some at the store a couple days ago, but that wouldn't surprise me. I mean, I am too, because like I said, it's not working yet. But also it's awkward because I get really excited and want to tell people about this hydroponic system I'm growing, and then they just want to talk about weed, and I'm like, no, that might be fun. Not there yet. Actually, I'm going to touch on that a little bit. But yeah, I just want to grow lettuce and not have to depend on the store for salads. So why not over-engineer something massively? I'm going to see. It's saying that host disabled participant screen sharing. Brian, can you fix that for me?
Let's hope so. Let me see. Security, maybe? Allow participants to share screen. There we go.
Oh,
okay. Yep.
So let's see. Probably look at. Does that look like my title slide? I can't really see it. Okay.
It
awesome.
does.
Okay, cool. Yeah, so we titled this one Hacking Hydroponics. I just sort of gave the motivation. Like I said, it's not quite done or working. There's still stuff to talk about. And then I wanted to start off by talking about engineer's disease. Has anyone ever heard this term? There's not really a canonical definition out there for it, but working definition I'm going to use is to assume that one's domain expertise in a given technical field applies to having expertise or authority in an unrelated field, right? And this can be anything from, a first-year engineering student, like not doing very well in a women's studies course, on to like actual engineers just being like, hey, cool, I'm a really good engineer. I should be a really good city planner then too, or expecting that the things that we do translate to solving social problems or anything in the humanities or something like that. And, this is something that I just want to make everyone aware of, and try to be sensitive of. Those are big problems. I bring it up in this case because I'm super not a hydroponics expert. I've read it a lot on this thing that I'm trying to build, but it's not built yet. So there's probably, it looks like there's only 5 or 6 of us here, but one of you probably knows more about hydroponics and or does it better than I do. So just wanted to start off by qualifying that I don't really know what I'm talking about. So this, less of a greater impact than the examples that I just gave, but and I can talk about the cool technical stuff, and that's probably the interest of this group anyway. But just wanted to say that I'm really not an expert, and I'm probably going to build the thing and it's not even going to work, and all my plants are going to die, and I'm not a good one to ask questions about this, but just want to manage expectations going in. That being said, sort of a talk overview. I'm going to talk about hydroponics, given my book knowledge of it, as I just talked about. Talk about what hydroponics is and what it's not. Then go into some of the techniques that are used by people. There are people that do this for a living. There's aside the whole cannabis thing, like a lot of strawberries and tomatoes are grown in this country and in other ones. Hydroponics is a big, actually like mature market segment. So I'm going to talk about some of the implementation details of systems out there that people use in home systems also. And then I'm going to talk about the system that I built and some of the design principles there, including a lot of applications of my experience as an industrial engineer with sort of industrial control systems, and that approach to systems control that goes a little beyond what I think the maker community is sort of used to and thinks about, like, oh, I'll just buy a Raspberry Pi, the answer to everything, right? But there are some engineering principles that you can apply to make things a little more professional, a little more fault tolerant, and that I think are just a better sort of mindset to bring to problem spaces like this that aren't really taught in college very much and aren't as out there in the world as much as I'd wish. So I'm going to try and get that out there. So that's a rough sketch of my talk that, by the way, I just finished about 10 minutes ago. So we'll see how this goes. Starting off with our intro then to hydroponics, what is hydroponics? And we'll just define that for now as growing plants without soil. Most of the plants that we're familiar with here on, the third of the planet that's dry land, most of the plants grow in soil. There are a lot of plants in the ocean, and we don't eat those very much. We eat the things that eat them, and they don't really grow in soil. We're not going to talk about those, but the plants that we do eat and encounter in daily life, they tend to grow in dirt, not on rock, not in sand, but in dirt. So if we're going to grow plants without that, let's see what it actually does for them. So what does soil do for a plant? Of course, the first thing it does is actually provide it physical stability, right? The roots grow down into the dirt, and then that holds the plant up. Some plants do okay, like falling over, but most of them not so much. So one function of dirt, right, is providing physical stability for the root system and for the plant to grow upon. So if we're going to grow plants without soil, we're going to need something to replace that. Also, right, the plants need water, and if they're not going to live in water full time, we just disqualified that entire entire set of the kingdom. The soil's a granular medium. It has a high surface area to volume ratio, so it retains water pretty well, and that water is then delivered to the plant's roots. And plants, without going into too much detail about plant metabolism, they hopefully know that they need water, right? Because if you don't water your house plants, they don't last too long either. And they get that through the soil. It also provides them with nutrients. Again, not going to go too much into their metabolism, but plants need things like nitrogen in the form of ammonium or nitrates. They need potassium, they need phosphates, they need other trace minerals to undergo their metabolism and get bigger and grow and turn into things that we can eat, right? And most of those, as I just mentioned, are ionic compounds. They're salts, so they're water soluble. So that tends to go, along with the water. That's going to be of importance to us in a moment. But they also need, the plant roots also need air, primarily oxygen. You think about plants needing carbon dioxide. They also need oxygen. Again, not going to go into the details of why that is, but these are plants that don't grow in the ocean, right? And the soil, again, is a porous medium, right, and allows oxygen to reach the roots. If that doesn't happen, the roots get slimy and they die, and then the plant doesn't do too well either. So those are, these are the principles of concern that soil, what it does for plants, and things that we need to keep in mind if we're going to replace them. So if we don't need soil, cool, let's replace it with some other media. And that can be, there are all kinds of engineered silicates like rock wool. You can use clay pebbles, you can use glass marbles, just some sort of granular media to take over that physical role. Again, it should probably be high surface area to volume ratio, so something fibrous or a silicate foam or something like that. There are all kinds of these things. I'm not going to go into detail there. Again, I don't have expertise. I haven't gotten too far with my own work because I'm building a control system instead. But you can see there in the image to the right, there's sort of that clay colored. Those are clay pellets in what they call a net pot. So that's just a piece of plastic with holes in it, right? And then there's just little clay pebbles in there that are porous, and the roots you can see have grown through that. The nutrients that we talked about are water soluble. So as long as we can get, the water, the nutrient solution to the roots, then we've checked off that set of requirements. But again, we don't want to deprive them of oxygen because then they die. So we'll get to how to sort of walk that line in a moment then. But this is hydroponics as defined that I want to be talking about, growing plants without soil in some sort of nutrient solution instead. Quick qualification then, hydroponics is not the same as the industry term is controlled environment agriculture. And that's even just greenhouses, as I've written it here, using artificial lights and temperature humidity control to determine the plant's environment. So that is often combined with hydroponics, but it's not the same thing, and it absolutely doesn't have to be, You can build a hydroponic system and set it outside. And we said hydroponics is growing plants without dirt. You can do that and you can set it outside and they still get natural sunlight and natural air, and they're still subject to natural weather, right? But that's a hydroponic system. Conversely, you can set up a grow room with lights and something temperature controlled, even CO2 enriched maybe, It's a totally artificial environment, but you can still grow plants in there in normal dirt, and that doesn't have to be hydroponics. This is, very commonly they are combined, but I just wanted to be explicit that hydroponics is just the nutrients and just not using dirt, and different from controlled environment agriculture, conceptually speaking. Just wanted to be safe on that. And then next we'll go into some of the techniques that are used. So we talked about wanting to get this nutrient solution to the plant roots, but not so much that they drown. And we didn't really talk about the details of doing that. And there are a few sort of system architectures that people have invented to do this. The first, and a lot of people starting off with hydroponics will build a system like this that's called a flood and drain system or an ebb and flow system. So we have our nutrient solution in a reservoir of some type, like a plastic tub. Those seem to be pretty common in the hydroponics world, and you can see those at the bottom of the photo there. Those are plastic tubs that are full of the nutrient solution, and that's a reservoir. And then there's some sort of pump that will periodically pump that nutrient into the little pots that the plants are in. So it'll inundate the roots, right? And they'll get flooded with the nutrient solution, and yay, they can uptake water and they can uptake nutrients. But again, you don't want the roots submerged all the time or they'll dry. So then you just drain off the nutrient after that, So I think a lot of systems like this will run like every hour, they'll flood the root zone for like 5 minutes or so, and then let the residual water just stay there, drain off the rest of it, and then the roots can get enough oxygen. And this is a formula that works, and they're pretty simple to build. Another system is called the nutrient film technique. And similarly, you can't see it in this photo, but there's a reservoir of nutrient. And there you, instead of sort of in the time domain and the space domain, you make it so you just trickle a little bit of nutrient through. So if you think, if you could see in those pipes, you'd see the roots dangling down, and the tips of the roots might hit the solution if there's just a little trickle going along the bottom, but the rest of them can breathe. The previous concern that we had talked about. So that's another sort of system topology that people build that tend to look, that you can see that looks pretty simple to build. It's a lot of PVC pipe and a lot of time with a drill. But then a pump and a reservoir, and cool, you don't even need a timer like in the previous case. An even simpler technique goes by the name of deep water culture, abbreviated DWC, where you have the plants, instead of growing in some long trough or something with the tubes that we saw, they grow in a bucket. And I can say this is the technical term. I've talked to a bunch of growers, and bucket is the technical term. Here again, it's a plastic tub. But here you have the roots, and you actually do have them fully immersed, both in the space and in the time domain. And wait, I thought we said the roots die if that happens. You can get around that if you, like, oxygen's the big thing there that we're looking for. So you just need to get oxygen into the water. And if you have a fish tank, you might know how to do that already, right? You just need to aerate the water with like an aquarium air stone. And then your plants will be happy enough without having to mess around with either of the previous concerns. So this is the simplest one we talked about, right? We don't need a timer, we don't need a pump, it's just a bucket. Well, we need an air pump, but we don't need a water pump. Sounds a little safer. And one drawback to this technique is that we don't have a reservoir. So realize that the nutrients are consumable, right? Because they're going to nourish the plant. So presumably the plant uses those up over time. And it might be a good idea to have a reservoir, right? Because then you have like a whole bunch of the stuff and they don't use it up as fast, or at least there's more for them to go through. If you just have a bucket like this, they go through it pretty quickly, and you have to tend to that, just dump more nutrient in. But your ratio of the volume of nutrient to plants is lower in this case, but you made up for it in simplicity. Combining the two techniques, you get one called recirculating deep water culture, where again you have the plants in buckets, and the nutrient is aerated, but it's also recirculated. So you do have a reservoir. The technical term is a control bucket. So hopefully you have enough volume, and then you don't have to adjust your nutrients as much. And these systems are really common in the commercial world. Like a lot of strawberries in the US are grown with a deep water culture system like this. So if you look in the commercial world, like this is a pretty winning technique. And it's more or less the system that I'm trying to build that I'll get to in a moment. And one other technique I wanted to mention is called aeroponics. And this, in deep water culture, we talked about oxygenating the water and getting our, you need oxygen and water. So you put oxygen in the water that way. Here you put the water in the oxygen with a spray nozzle or the transducer from an ultrasonic humidifier, right? And you just get very fine nutrient mist droplets into the root zone. So NASA is big on this one. As you can imagine, there's less volume of nutrient there. It doesn't weigh as much, and that's probably better for space applications. It is a little more technologically difficult because you need if you're using misting nozzles, you need a high pressure pump. And those are a lot more expensive. They're a lot noisier, and they're a lot more difficult to plumb than the other examples we talked about that are just using a circulating pump. When I talked about the ebb and flow and the NFT and the recirculating deep water culture systems, right? Those just need a circulating pump. It's basically, what would drive a garden fountain or an aquarium. There's not much pressure involved, but if you're talking about generating a mist, you need a burlier pump. They're noisy, they break, they're harder to plumb. These systems are also fault intolerant because those other three techniques we talked about, the roots were mostly wet most of the time. With an aeroponic system, if your misting mechanism stops working, the roots dry out and your plants die really quick. And there is a commercial solution for these called AeroGarden. I'm going to talk about those in a minute, and that's what's shown in that illustration. You can totally go to the store and buy, it's called an AeroGarden. It sits on your counter, it does all the work for you. And they're pretty cool. Technically, that's an aeroponics system. Again, more about those in a moment. Another quick aside, just to make sure we're technically correct about things. I wanted to talk about two different modes of plant growth that are called vegetative versus flowering. I talked about I want to grow lettuce. In some plants, the useful part is just the stalks or the roots or the leaves or something that pretty much all things we recognize as plants have and grow. There's another category of things or a category of plant-based products that require the plant to flower, and that's any sort of fruit that it generates. Right, so strawberries, you don't get strawberries until the strawberries flower. Similarly with nightshades like tomatoes or eggplants or peppers, right? Those are fruits, and the plant has to flower before they grow the fruit, and that's sort of a different thing from the plant just growing itself, right? So it gets to a certain size, and that's not to say it stops growing, but it puts out flowers, and those flowers turn into fruit, and the fruit has seeds in it, and that's how the plants reproduce. Like I said, there's another plant product that's just the flower. Well, there's decorative ones. There's another one that's big in this stage, but that's using plant products from after they flower. And you can recognize that that's, kind of a qualitatively different thing from the plant just growing vegetatively and getting bigger. You might think, and it turns out to be the case, that the plant has different environmental requirements. Because they flower at some point in the season, so maybe they're looking at the sun to determine when they're going to flower. Growing fruits, they tend to be sugary or sweet or something. You might think that requires different nutrients or something. All of that turns out to be true. So the system that I'm working on is just for lettuce, herbs, like leafy herbs, onions, and stuff like that. So I don't have to worry about that, right? Like the plants grow the same way all of the time. If you do want to grow strawberries or tomatoes or weed, that's something that you need to worry about. And you need to run them through cycles, and the dimension of your problem space just goes up hugely. So as I said at the beginning, I don't know what I'm doing to begin with, and am correspondingly just going to, not worry about growing tomatoes or strawberries. Like, all of that sounds just too complicated. I'm going to just see if I can get anything to basically grow. But just to make you all aware, that is a big concern, with commercial systems, is when to kick the plant over from one growth phase to the other. Cool. So like I said, you can buy these things called Aero Gardens. They're totally cool. I've got a couple of them. They make them in various sizes. Entry models, like maybe $50, like a decent sized one's like $100. I think they have like bigger ones now. But they're pretty cool. They give you little like seed pods that just drop in there. And there's a little microcontroller, and there's, buttons and a little display, and the display is like, hey, I'm low on water. You need to put more water in. And by the way, you need to dose me with more nutrients in like 5 days. And you can set the light cycles like that. And then they mostly just generally work. They're pretty cool. Like I said, they want to sell you the seed pods that drop in there, but you totally don't have to buy them. The internet's replete with how to reload the ones that exist, with whatever seeds you want to grow. They'll like sell you the replacement equipment, like third party. So you're totally not tied to the sort of Keurig business model that the company is trying to force on you with these. The problem is the controller in there is like pretty smart, but you don't really have access to it. I'm sure by now some of them have Bluetooth or Wi-Fi or something, and oh cool, get our app on your phone, and then it'll remind you when it's out of water and stuff like that. But you don't really have access to the low level mechanics of the machine that I imagine would be of interest to anyone who's still with us in this conversation. But they're cool. They're, totally recommend them, for like a countertop or garden or growing lettuce or something like that. Like, these are great. They're not paying me to advertise, but they're pretty cool, and you don't have to fall into their consumables based ecosystems. Not really the word to use, but yeah, anyway, Aero Gardens are cool. If you're like a maker inclined person, you're going to build something like this that I'm calling the Arduino monstrosity. And okay, cool. I do want to, do the low level stuff, and I want to see what the sensors are doing. And, I do want to run the pumps on my own. And, cool. You built something like this, and you tried, and you're trying to work from first principles, and that's pretty cool. The one in the photo is like kind of a little small. I don't think those are even food plants, but if they were, you wouldn't get much food out of them. So it's kind of little, and also don't sneeze. And this is where I pause for my tirade. Because look at that thing. Everyone that builds stuff out of Arduinos builds something like this. And it's cool. It's great to be able to build stuff like this. Like, that goes great on like the bench when you're taking a microcontrollers class in college. And everyone should do that, by the way. But if you want this thing to last longer than like 2 days, what happens when your cat jumps up there and starts trying to eat the plants and then knocks the board on the floor, right? Like the little leads that are stuffed into the proto board, like, it's not mechanically robust. The software is probably not that good. Because what's it got to do? It's got to, run these different actuators. It's got to turn the pump on and off, and it's got to, probably monitor some sensors, and there's a display on it, or maybe it's doing network activity, so it can tell your phone like what it's up to, or so you can check it on the road. What happens when a network call gets hung, right, and it leaves the pump turned on or something like that. If you want something that's going to be robust, right, you probably didn't catch a couple little conditions still get stuck in, like your software for it is probably not as good as it needs to be if you're just writing bare bones, Arduino, like init function, loop function. stuff like that. Unless you're like a serious embedded developer, I totally advise against building stuff like this. Again, it's totally cool. It's good. People are you know, definitely lowered the barrier to entry versus where physical computing was at 25 years ago. But I find stuff like this, again, this is my thing. If you saw my talk at the unconference a couple of years ago, this is totally my thing, that it's kind of chintzy and it's not harder to do better. So with that being said, that being the Arduino monstrosity, here's the thing that I'm building. And it's bigger and burlier. Like I said, it's not finished, you know, pretty obvious there's no plants in there. But a couple of photos of how this is built. It's on a wire rack, like a ladder rack shelving unit that's 48 by 18 inch, I think. The ubiquitous plastic tubs there with a nutrient reservoir on the bottom and then the growth tank up top. So this is meant to be a recirculating deep water culture system. So I haven't built it yet, but there will be a styrofoam raft that holds the net pots and just floats on top of the nutrients in the upper tank. The reservoirs there on the bottom. You can see a solenoid valve and all of the bunch of wires that aren't hooked up yet, but there's a valve to drain the top tank into the bottom one there on the side with the little like red cap on it. And then there's a submersible pump to pump the nutrient from the reservoir up into the top tank. Just because I was kind of proud of these, there's a little 3D bracket I made in the upper right to hold a couple of the float switches. I'll get to why those are important in a minute. And then the general electrical panel, because I figured that would be of interest to people. It does have Ethernet because the controller that I used uses copper Ethernet. I'll get to why that is in a minute. There is a Raspberry Pi on edge, 2 units over from the left there. Excuse me. With a USB hard drive, its little power supply. And then the bottom rail there are the power supplies for it and a bunch of power distribution and interconnect stuff. With the little cable trays, so all the cables, I put the cover on the top one, but all the cables live in there, so the wire management, at least until you take the covers off, looks pretty nice. Everything's screw terminal, right? So the cat can jump up there, he ain't gonna break anything, because everything's pretty solidly screwed in. Instead of the leads just going into the proto board that we saw previously. I wish more people would build stuff like this. This is how, you know, a lot of industrial equipment is built. It's very modular, it is robust, and it's not a whole lot more expensive, and it's not much more difficult to do than the sort of tabletop microcontroller stuff that the maker world does these days. But it's a lot cooler, and it's a lot more fault tolerant. And the rest of my talk, I'm going to go into some details of what this sort of design perspective looks like. Starting off, here's what in the industrial world is called a PNID. That stands for a piping and instrumentation diagram. And this is sort of the hydraulic and chemical process equivalent of an electrical schematic. And there are standards for what these symbols mean, and you know, I've abused a lot of them, like you tend to. But this shows, you know, where the pipes go and where the instruments go. Instruments being, you know, float sensors, like I talked about. So the growth tanks up top, the reservoirs down below. The growth tank has 3 float switches. They look kind of like record needles. Labeled I3, I4, I5, and those are float switches. So they, you know, there's a little bobber with a magnet on it that is hydraulically isolated from a magnetic switch. And as the bobber moves up or down, it contacts or opens the switch. And you can get a bit of information then, yeah. The I is just a convention from the industrial controls world. I is a bitwise input. I also have an analog input, and there's an analog level sensor in the reservoir, labeled as AI1. And that, let's see. I want the float switches, because I want to, turn off the pump if the reservoir is about to overflow. That makes sense, right? We talked about we want the reservoir bigger than the growth tank, so we don't have to change nutrients as much. But if your reservoir is 20 gallons and your growth tank's 5 gallons, and you try to pump all 20 gallons into the 5 gallon space, you end up with 15 gallons on the floor, and that's bad. I also bought the cheapest Amazon float switch as possible. You can buy good ones, they're like significantly more expensive, or you can just buy cheap Chinese crap. And because that's a really bad failure mode of pumping the entire reservoir onto the floor, I have 2 of them up there, so they both have to fail before we hit that failure mode. Yeah, quick talk on failure modes. That's the bad one, is pumping the reservoir onto the floor. That's what I don't want to do. Sort of not as bad as letting the growth tank grow dry for an extended period and then the plants die, and that's we don't really want that to happen, but that's pretty survivable. Also, the pump is under digital control, also as Q2 down there on the bottom, and like I said, that's a submersible pump, and they're cheap, but they do depend on being submerged for cooling and for lubrication. So another failure mode, if I seriously didn't pay attention to the thing and we used up all the nutrient and it dried out, we wouldn't want to run that pump when it's dry. That's another known failure mode. So it's mostly those 3. Again, pumping the reservoir onto the floor is the worst thing we could do. Known failure modes then are the plants die, or we burn out the pump. And of known failure modes, those are the 3 that we're worried about. This aside from like shoddy wiring, like burns the house down or something like that. But all of this, be careful with it. These are if you're thinking in the industrial controls world, and again, makers don't tend to think this way because they just got their little thing that the cat knocks over anyway. But fault conditions like that, good things to think about when you're building a system like this. Where was I? The pump that pumps the reservoir into the grow tank, like I said, is digitally switched as Q2, Q being a convention for output, bitwise output, sorry. Q3 is a valve that opens to drain the top tank back into the reservoir. And then I also have Q1 is controlling the grow lights. Let's see if I can go back. You can see I have fluorescent tubes. I got those from a friend when he decided he didn't want his fish tank anymore. And they happen to fit my form factor pretty well. But those are also switched by the controller so that I can, with the same control system, instead of some separate electromechanical timer or whatever, I can turn the fluorescents on and off throughout the day as might make sense. Like I said, the reservoir level is analog because as the nutrient gets depleted, I want to have better than just a bitwise sense, right? So the float switches are, pump some water in here because I'm too low. Don't pump anymore because I'm about to overtop. And that's fine for the growth tank. Like I said, there's a raft, so the plants will just float on it, and they don't really care as long as we keep within those limits. You might want to know how much total solutions in the reservoir though, right? So you can, look at the rate of decrease and be like, oh, cool, I'm gonna need to top that up in 2 weeks or so. So that's our one analog input to the system, is the reservoir level. Everything else is bitwise. And sorry, I misspoke because we also have 4 temperature zones. So there's a temperature sensor in the reservoir, in the growth tank, near the lights and then far away from the lights, because the lights get hot and I want to know what temperature it is in the room. That, I said I wanted to have the light system under the same control as this. I don't want to have the room climate under the same control, like the house thermostat takes care of that. But I probably do want to know what temperature it is. If you look at control systems, temperature monitoring is really cheap. Temperature control is a little more expensive, but temperature sensors are really cheap. And they tend to be really good at indicating other failure modes. If some switch did go out or something, you tend to see like, oh, wow, this should be colder than it actually is if it was wet. So it's probably not wet. So if you look at any sort of industrial system in semiconductor processing or chemical processing, oil refining, water treatment, anything like that, they tend to have temperature zones like all over the place because it's just good data to have. Not under control is the air compressor, right? So we have just an aquarium like air pump going into aquarium air stones. And we're just going to have that on all the time. The general idea then, like I said, this is recirculating deep water culture. So the plants their roots are submerged all the time. So we have to aerate it. That's what the aeration system is for. But we do want to change out the nutrient. And I haven't decided, again, I hope this is even going to work. But my thought was probably to run the pump once an hour or so for 5 or 10 minutes so as to not have it on all the time. But then open the drain valve as needed so that we don't, overstep the limits from those switches, and we get mostly a circular flow, so the nutrient balance in the growth tank doesn't get too far away of what's in the reservoir. Haven't seen a system like this, but I think it'll work. We'll see. TBD. If we don't get a speaker next month, maybe I'll come back and let you know how it works. So cool. Let me talk about the control topology. And this is, I hope this is interesting. Again, this is what I want to impress on people. Because like I said, if you're, if you're writing Arduino code, it's great for like an appliance. And if you're an embedded developer, you're probably pretty good at it, but there's kind of a lot going on here, especially if you have network requests. Similarly, though, if you're trying to use a Raspberry Pi that's like a 32-bit system, running under a Linux kernel, you don't have real-time control. Because you don't have control over the interrupts. The Linux kernel takes that. So if you want to do something like turn the pump off, you just got to wait until the kernel task scheduler flips your bit. And people that do actual industrial control or actual embedded design are terrified by the idea of using the 32-bit Linux system instead of a microcontroller running a real-time operating system, an RTOS. So we solved that by physically separating concerns and using different modules for this. And the module that people here probably aren't, well, I'm assuming aren't familiar with, is called a PLC. That's drawn in purple there. We are using a Raspberry Pi as what we call a SCADA for that component of the system. And I'll get to what each of these are and what they mean. All of the stuff in pink are the actual sensors and actuators, right? So in the controls world, these are thought of as different levels of concern. Level 0 is what they call field devices, right? So the actual control over whether the pump's on or off, the actual control of whether the lamp's on or off, what the valve's doing, what the float switches look like, where that analog level is on the level sensor, and those DS18B20 is the part number of the temperature sensor that I'm using. So again, those are the very lowest level things you can get. They're easy to swap out, right? They have nothing, no intelligence to any of those devices. The level 1 device, like I said, is a PLC, stands for Programmable Logic Controller. And that's a level 1 device that you can see like takes all of those field device concerns and then bubbles them up to the SCADA, which again is a Raspberry Pi running this thing called PySCADA, which, like everything in the Python world, is just Pi stuck in front of what it actually does. Sorry, PHP group. I am a Python developer, so I grabbed that one. It's written in Django. I haven't actually messed with the source code because I don't have to, but I'll show you what that does in a moment. But as I was saying, you know, there's a lot going on here. So we start by breaking it out, you know, and are we talking about like the state of a switch, or are we talking about something that's running a web server, or something in between? And those are, roughly speaking, these 3 levels we're talking about. So this thing called a PLC, again, stands for Programmable Logic Controller. These are used all over the industrial world, have been, you know, the general principle goes back probably 50 years. And there's a picture of the one that I'm using there to the right. It's got a Siemens logo on it. That's pretty hardcore, right? That's a, you know, well-known, reputable industrial systems manufacturer. These things used to be pretty expensive. These Siemens logo units you can get on eBay now for like $100 each, which is still more expensive than a lot of hobbyist crap. I say crap, you know, it does have its place, but that's still not too expensive versus what you're dealing with using like a straight Raspberry Pi based system, you know, or an Arduino based system. Because you buy the baseboard, right, and then you realize like, oh, cool, this thing takes CMOS, like 3.3 volt signals or 5 volt signals, and I want to turn a light bulb on and off. So I'm going to need some sort of relay. I'm hitting my bullet points out of order here. But these PLCs tend to run on 12 volt or 24 volt logic. So they'll drive relays just fine. You don't need any sort of insulation or isolation or a lot of the concerns you have with simple microcontrollers. Like, these things are robust, they're built for mechanical environments, and they'll work with the sort of voltages you have in a real system, no problem. They do have deterministic timing and output state, you know. If you've ever messed with Arduino or Raspberry Pi stuff, because of the way those microcontrollers are built, when you turn them on, they tend to come up in either an unknown pin state or not the one that you necessarily want, right? In PLCs, you can totally program and just be like, hey, yo, when you turn on, this output needs to be high or this output needs to be low. And there's not sort of a startup transient that'll get you into problems there. They're not the easiest things to work with, though. You can see it's got 6 buttons on it, and a little dot matrix LCD. You really don't want to be sitting in front of that thing, like trying to page through it. It does have, it says LAN, right? And it does take it does have an RJ45 jack. It does not DHCP. You have to set its IP address by hand with the 6 buttons. It's as bad as trying to get your Sega Dreamcast on the internet was 20 years ago. But once you set it up, it's good and they just run, right? And that's what it should do. Going back to our 3 tiers here, you know, that purple box is just saying, okay, cool, I need to run this pump, but not if this switch is thrown, you know, or as soon as this safety mechanism trips, I need to do this. And I'm speaking in general terms because, again, these are used all over the place. These are used for controlling elevators. These are used for controlling oil refineries, stairwell lighting, right, where you have like this motion sensor trips and you want to turn the lights on that floor, and not, you know, they are programmable through, you know, probably not any programming language you've heard of. It's generally something proprietary and awful, but it does what you want it to do, which is very deterministic mapping of input conditions to output conditions, and then exposing that to a higher control level through in this case the LAN. That'll feed into our tier 2 then, which is what we called SCADA. Supervisory control and data acquisition is what that kind of gross word stands for. And you can buy, you know, like that was a PLC unit, you can buy SCADA units and they're really expensive and they're even worse to work with. But the idea is that those aggregate over the tier 1 devices. So that was Ethernet, right? If I had 10 of these systems, I could still use the one Raspberry Pi, and I could have 10 PLCs, each doing the control tasks that they need to do. And as long as they're all plugged into the same Ethernet hub, the same Raspberry Pi can accumulate data from all 10 of them. So that's the sort of benefits of this architecture. In the industrial controls world, it's called an HMI, which is human machine interface. Lately, that's frequently just a web page, right? You often get like that PNID, the diagram I showed. A lot of SCADA systems will allow you to just map directly the process variables to a diagram like that. They will interface with something called a data historian. That PLC is just concerned about like the now, right? It might have a timer, but it doesn't really care about what it was doing a week ago. If you are running an oil refinery or a manufacturing facility or even a hydroponic system, you might care what it was doing a week ago. That's not the PLC's concern, but you want to store historical data at this control level, at that tier 2 control level, right? And it is supervisory. You know, you might be able to tell it to do stuff. You know, the operator can say, hey, I want to turn this motor on or something like that. But it's not doing any actual control tasks and saying like, well, I can't turn this motor on because this sensor, you know, it's not monitoring any sensors or not making any actual command decisions. That being pushed down to the tier 1 devices. On my diagram, it is doing the temperature monitoring without an actual level 1 device there. And that's because we're just monitoring the temperature. Raspberry Pi has a bus controller for what's this protocol defined by Dallas Semiconductor called one wire. And those temperature sensors for, you know, they're like $1 a piece, unpackaged. In an environmental enclosure, they're a couple bucks more and they plug right into a Raspberry Pi. Since we're just accumulating data, we don't have an explicit tier 1 device there. If we were doing actual temperature control, which you do in a lot of, you know, chemical processes and things like that, also in like backyard grilling or sous vide or home brewing, you might need a closed loop temperature controller with a chiller or a heater on it. And that probably would be a purple device, but it would fall into this architecture the same way. That's a level 1 device, and the SCADA can just pull it. You know, we just don't have application for that in our particular hydroponic system, again, because the environmental controls out of scope. I talked about then that one wire protocol, the protocol that the PLC uses to talk to the SCADA, and this is my last slide, something called Modbus. And this is a really old protocol, but just wanted to make people aware of it. This is like 40 years old, seriously. That's, you know, ASCII wasn't even really standard back then. But this was pretty revolutionary at the time, and it's like built to enable this. I'm like, cool, I have this guy with this domain of concern, and he needs to know what this relay state is from a separate device. There's a protocol called Modbus that hopefully you never have to actually deal with, like at the bitwise level. But if you want to find out conditions of bits or words, it gives this register framework, so you can sort of abstract that and just deal with them by addressing. It works over either physical serial layers, or as I'm using, like it transparently tunnels over TCP, and I don't have to care about that once you set up the IP address of the little guy. It just works, and then it can say, oh, cool, is the light on? And it knows that, and you just program that in the PySCADA. Which I wish I had time to show you, but it's super not built enough to be interesting. And then I just wanted to mention that there are alternative protocols that are a little more modern. I talked about OneWire. There's also SNMP. This is used in data centers a lot for checking like the UPSs and all the HVAC concerns that, you know, big computing clusters have. One called CAN bus stands for Controller Area Network. That's used mainly in automotive applications lately. BACnet is, I think, building automation controller. And there's one called VISA, which is virtual instrument software architecture. So these are other protocols that, again, you might not have heard of. They tend to be transport layer agnostic, but just allow a high level way for a SCADA system to talk to its other controllers and just be like, hey, cool, what do your inputs look like? What do your outputs look like? So I can chart them and present them to the operator. I tried to come up with a conclusion slide then. But next steps on my system, first priority, of course, is to get it working like at all, which it's not yet. I want to get some plants in there, see if they survive. At that point, like I said, this is pretty scalable, right? So I have a big reservoir and a small grow tank. I can get more small grow tanks. I just need another ladder rack and some more lights, right? And I can put another couple bays in it. So that's one of the next steps I might take. Another thing I'm thinking about is adding a controller to take care of the nutrients. So I didn't get into detail of what the nutrients look like, but there are totally systems out there. And again, you can buy one off the shelf or you can roll your own. Guess which one I'm going to try to do, to check and look at the nutrient concentrations, look at the oxygen level, run little micro dosing pumps that will compensate for pH differences or, the nutrient levels low and stuff like that. So that's something I want to play with too. Again, it'll generally fit into the same control architecture, since the SCADA is sitting there at top level and that's serving the web page that shows me what's going on. It's, doesn't require a major system redesign to just bolt on that set of controls and be able to do that. So that's the benefit of, again, as compared to just buying something totally off the shelf, which nothing wrong with that, but if you're the sort of person who only does that, you're not here. Or compared to doing a little benchtop project with a single microcontroller like an Arduino or a Raspberry Pi or a BeagleBone or whatever. I just wanted to try and make a case for that 3-level architecture where you've got, robust, hardened, noise immune, environmentally rated, serious industrial stuff. And you have your domains of consideration carved out between them with a top supervisory level. And, architect your system like that, you'll have room to grow into it. That's my conclusion. Went a little over time there. Didn't know this was going to be quite an hour, but thanks for everyone bearing with me.
Yeah, thanks, Drew. That was awesome. That definitely did not disappoint. Thank you very much for doing that. And let's open up the floor to questions. Does anyone have questions for Drew?
Well, can you say what was the gist of your unconference talk that you were saying at the point you were making about the industrial equipment versus the Arduino monstrosity?
Boy, it is not worth my digging out those slides. But really, it was pretty much the same thing. So it was the point that I was making was pretty much the same. And that system was what they call stack lights, which are another thing from the industrial world. You see them on like self-checkout counters where there's a little like stack of colored lights on top. And it is, you know, it's supposed to like turn red when something needs attention. That was my situational awareness enhancement device, right? I just built something that had like 5 of those. And I turned it over, to the ops guys. I'm like, hey, hook this up to CI/CD, hook this up to like our security monitoring or something. Like, I don't, there's five lights that can be green, yellow, or red. Make it do something interesting so we can know how our builds are going or whatever. A lot of shops have this. So the point that I was making was just, kind of similarly how to architect it. I did just use a Raspberry Pi, but it used a hat with little screw terminals, so it was all screw terminals. There wasn't one of those cribbage boards. It used terminal blocks. Everything was screwed down, so it was pretty mechanically robust. And then just making a similar point then of know your problem domains, so here's a little loop that's going to run as its own process. And it's going to make sure the light is the correct color, right? And that's its only job. And that feeds off some layer that's then, I forget what, it was Google Firestore actually, was the transport layer there. So there was a cloud-based serverless API, and it was just like, cool, hit this URL, tell the light which color to be. And that layer ran serverless, updated a Google Firestore, which has asynchronous updates. So then there was another stack layer that was receiving those async updates from Google Firestore. And then actually on the file system, just by whether files existed or not, told that lowest layer what color the lights should be. So a similar point of you get into trouble if you try and mix all of those concerns, right, and run a web server that's then issuing the port commands to change the light colors, to try and break it down. Make one thing that does just what it's supposed to do, does it well, and then talks to other layers in the stack. That was mostly the point of that talk, kind of similar. And then another point about, seriously use screw terminals, use the cribbage board to prototype, but either, cast that in resin or put it in a locked box or something. Don't count on that being mechanically robust, and just, think about your architecture before you get to build it. Hope that answers your question.
Yeah, cool, nice.
I just wanted to say thanks for sharing it. I appreciate the intro that you gave, that you said you didn't know a whole lot of hydroponics, but I would argue that great strides in any field usually come from people who think they don't know anything about it.
Yeah, thank you. Like I said, that was all book knowledge. I don't really consider myself a Redditor. I read like really specific subreddits, and /r/hydro is the basis of most of my knowledge about this. That's very different from having actually done it. And I just wanted to be careful about that. It's very likely I'm going to plug it in. All the plants are going to die. It's going to get some gross fungal infection. It's very likely I'm going to get bored and move on to something else before I even finish it. But yeah, thanks. I sound like I know a lot, but I just wanted to make really clear that I'm not some seasoned, this is my 20th hydroponic system. Ask me. I was mostly just trying to fend off questions, someone just being like, oh, hey, cool, I built this and this, like, why is my tomato brown? I'm like, seriously, I don't know. But hopefully it works, again, if, this is my first time with this meetup, I'll hopefully come back and maybe give you all some updates if there's anything interesting development-wise down the road.
Yeah, awesome. Any other questions? Seeing none, let's thank Andrew again. Again, fantastic. I'm still blown away. I did record this, and of course, I didn't ask Drew beforehand if I could post it to YouTube, but I'll ask him after the, after we get off the call. I'll make sure it's okay to post to YouTube, and assuming it is okay, I'll share the link with the meetup, and you can watch it again and again and again, as many times as you need to get down, everything he said about everything he said. I mean, it was all great. And if you want to be the presenter for next month or a future month, it doesn't have to be something, obviously it doesn't even have to be something that's done yet. It doesn't have to be something polished. It could be something that you're doing in your spare time, that you don't know if it's, the greatest code in the world or, associate programmer level quality. It doesn't matter. If it's something that you're excited about and you're proud of doing, we'd love to give you a forum to share that with the group, and just promote doing cool stuff with tech, and not just going into an office and hacking on the keyboard for 8 hours a day, because there's some really awesome stuff that we're doing, and it deserves to be known. So if you want to be that, you can find me on Meetup. Let me know if you want to say something now. If you have something that you have in mind that you want to present, let me know, and we'll get you on the schedule. And I'm really excited to see what we're all building.